All right, guys, Mr. Antonucci here, and in this video, we want to talk about how to calculate the standardized test statistic and p-value for a test about a population proportion. So the standardized test statistic measures how far a sample statistic is from what we would expect if the null hypothesis were true in terms of standard deviation units. In other words, the standardized test statistic is equal to the statistic minus the parameter divided by the standard error of the statistic. Okay. Now, the formula sheet for the standardized test statistic is included on the formula sheet on both sections of the AP exam. Now, in most cases, we're going to be using sample data to estimate the standard deviation of the relevant sampling distribution, which is why the formula uses standard error instead of standard deviation in the denominator. The only exception is a test about a population proportion, where we're going to calculate the standard deviation using the hypothesized value of the proportion P naught, not the sample proportion P hat. Okay, now a footnote on the second page of the formula sheet addresses this special case. And as we previously learned, the formula for the standard deviation of p hat is on the formula sheet as well. So you can use the standardized test statistic to find the p-value for a significance test. Now, we can look here for how to calculate the standardized test statistic and p-value in a test about a population proportion. So basically, we just suppose the conditions are met. We don't just assume it. It's either stated in the problem that those conditions are met, or we previously had to check them to perform the test of null equals p to calculate the standardized test statistic. So basically getting the z-score. So you have p hat minus p naught. Remember, p naught stands for the proportion assuming the null was true. So it's the proportion from the null divided by the square root, and this would be the standard error of p naught. So we found the p-value by calculating the probability of getting a z statistic as large or larger in the directions specified by the alternative hypothesis, HA, in the standard normal distribution. So if we want a less than or a greater than, because some types of significance tests don't use a standardized test statistic, some people use the more general term test statistic to describe the value of z in a significance test about a population proportion. So let's look here at an example. So piggybacking off the example in the previous video, we had that administrator at a large high school. He wanted to perform a test at the significance level of 0.05, where the null was the proportion of students have a part-time job is 0.25, and the alternative is the proportion is less than. So we already confirmed that the conditions for performing the significance test are met. So here we're going to do the next couple of steps. So we want to explain why the sample result gives some evidence for the alternative hypothesis. And here is where you're going to want to write basically a sentence or two. The sample proportion of students at this school with a part-time is p hat, not a Joby, equals 43 out of 200, which is 0.215, which is less than the national proportion of p equals 0.25. Okay, so again, we got a sample that had a sample proportion less than the national average or the national proportion. So this is some evidence for the alternative hypothesis. But the question we eventually want to get to answer is it convincing evidence? So first thing we want to do is calculate the test statistic and p-value. So for this one, Z equals 0.215, that's our p hat, minus p naught, which is 0.25, divided by the square root of p naught. Remember, we use the the null value, not the sample proportion, to calculate the standard error here. And we get negative 1.143. So if we think in terms of a graph here of the normal distribution, okay, here's 0, 1, 2, 3, 1, 2, 3. Negative, this is negative 1, so negative 1.143 is going to be right here. And since we are doing a less than, we want to know the probability of getting that result or more, or less rather, not more. So in order to do this, we can use table A. So this is the z-score, or this test statistic. And to get the p-value, we can do table A. If we look up on table A, you would get 0.1271 from table A. And you don't have to subtract it from 1 because the table gives the left side distribution. From technology, we're going to go ahead and figure that out right now using our graphing calculator. So you go second distribution, normal CDF, we want the cumulative density function. Since we're doing a left-tailed, we go negative 1,000, comma z-score, which is negative 1.14143, comma mean, standard deviation of 0 and 1. Okay, close that off, and you get 0.1265. So either one of these would be acceptable for the p-value. So for part C, we want to interpret the p-value. Now this is important, and the wording is very critical here. You want to make sure that you have the same type of structure that we have in this example, and also you want to use your numbers in context of the problem. So what the p-value is it's assuming that 25% of all students at the school have a part-time job. Okay, so we assume the null is true, 0.25. There is a 0.1265 probability of getting a sample proportion of 0.215 or less by chance alone. Okay, so basically, if the null was true, if the real proportion was 25%, or percentage was 25%, have a part-time job, then if we took a random sample of 200 people, um, we would have basically a 12.65% chance of getting a proportion this low or lower by chance alone. Okay, so we're looking at how likely we are to get the sample result. Because remember, you have sampling variability involved here. Now, notice that we did not use technology to find the desired error without standardizing when performing the normal calculation in part B of the example. That's because you're always required to give the standardized test statistic along with the p-value when performing the test on the AP Stats exam. So we didn't skip right to the p-value, we showed what the z-score is, or the standardized test statistic was first, and then calculated the p-value there. Okay, so um, you can use the TI calculator to perform calculations for a significance test about the population proportion using this example that we just went over. So if we go back to the graphing calculator, so what we do is, let me just clear this stuff off. Okay. You hit stat, and then we scroll over to tests, and um, we want a one proportion Z test. So that's this one right here. We hit enter, and then we put in the values. P naught is the null value, so that's 0.25. X is the number of successes, essentially, so 43 in the sample. N is the sample size, 200. And then these inequalities down here are the kind of test we're doing. So we're doing a one-sided test. It's going to be less than. So this should just match your alternative hypothesis. And then calculate. So the results here um, we have are the proportion less than 0.25. Here we have a z-score of 1.143, a p-value of 0.126 for time, blah, blah, blah. And it gives us our sample proportion as well as the sample size there for this problem. Okay. So we want to talk a bit about two-sided tests. According to the National Center for Health Statistics, 36.6% of US adults eat fast food on a given day. A public health director wants to know if this holds true all for all adult residents of a particular country. So random sample of 150 adult residents finds that 68% of the residents ate fast food. Now, because p hat in this case is 68 out of 150, that's 0.453. That's different than the national average. I know it's greater than, but we're just going to say it's different at this point. There is some evidence for the alternative hypothesis. Um, he wants to know if this figure holds true. So our null would be that P equals 0.366. The alternative is that P is not equal to 0.366. And this is how you would set up a two-sided test. So we want to see how likely it is to get something this different or more different from 0.366 in samples of 150 adults by chance alone. So to see how likely it is to get a sample proportion this different or more, we need to basically find the probability of p hat being greater than 0.453 and the probability of p hat being less than or equal to 0.279. Now, the reason it's greater than 0.453 is because 0.453 from our sample is greater than the national average. But if you take the difference between those two, you would get 0.366 minus, or excuse me, 0.453 minus 0.366 equals 0.087. So we were 0.087 above the national proportion. So we had to go that much below the national proportion. So if we subtracted 0.087 from the 0.366, that's where the 0.279 came from. Okay. So if we look at this graph here in part A, The national average is assumed to be the proportion, so that would be the middle. And then we want to know um, how different our sample was. So we got 0.453, which is up here. And then on the other side, if we subtract 0.087, we get 0.279. So um, to test the null versus the alternative with this particular p hat, we would have z equals 0.453 minus 0.366 over square root 0.366 times 1 minus 0.366 all over 150, our sample size. And this is going to give you about 2.212. So right here, this is the standard normal distribution. And that is the shaded area to the right is the P is the probability of getting that z-score or z standardized statistic or more. But also we have that amount on the left side there because we need to figure out um, the probability in the other direction because it's a two-sided test. And because of the symmetry, we can find the area in one tail and just multiply it by 2 to get the p-value. So if we want, using technology, we can get the p-value of z greater than 2.212, which is 0.0135. That's this right here. So the p-value is equal to 2 times 0.0135 because we have to account for the other side of the two-sided test. So this is going to give us 0.027. So what's this result mean? Well, assuming 36.6% of all adult residents in the country eat fast food on a given day, there is a 0.027 probability of getting a sample proportion of at least 0.453 or at most 0.279 by chance alone. Now, since that p-value is less than our significance level of 5%, we would reject the null and conclude that there's convincing evidence that the proportion of all adult country residents who eat fast food on a given day is different from the national proportion. Okay, and then the last little bit is just about how confidence intervals give us more information. So knowing that the proportion of all adult county residents who eat fast food on a given day is different from 0.3666 is interesting, but it doesn't give much information about the population proportion to the county health director. So a confidence interval can actually help in situations like this. So in the previous section where we found 95% confidence intervals, we could do that here in this case by simply taking the sample proportion, 0.453, and adding or subtracting the critical value, 1.96 for a 95% confidence interval, times the standard error, which is 0.453, 453 over 150. Now notice here to get the standard error, we're using the sample proportion because we're trying to construct a confidence interval about the sample proportion to get a range of plausible values for the true population proportion. Okay, so this is 0.453 plus or minus 0.80, which is going to give us a confidence interval of 0.373 to 0.533. Okay, so we are 95% confident that the interval 0.373 to 0.533 gives the true proportion of adult residents in this county who eat fast food on a given day. Okay, so the health director should not be surprised if the population of all adult residents in the county is between these two values. It would be surprising, however, if the population proportion were any value outside of that interval. Now, here's the link between confidence intervals in two-sided tests. The 95% confidence interval we have right here gives an approximate set of values that are plausible for um, P naught that should not be rejected by a two-sided test at the 5% or 0.05 significance level. Any value of P outside this interval, including our null value of 0.366, should be rejected as implausible. Now, with proportions, the link isn't perfect because the standard error used for the confidence interval is based on the sample proportion, while the standardized test statistics denominator uses um, the null value for that. Okay. But the big idea is still worth considering. A two-sided test at a significance level of 0.05 or 95% confidence interval gives similar information about the population parameter. Okay. All right, guys. Hope that was helpful to you. Take care.